Second part of rules of integration. So last week was an introduction to integration. Just giving you the basic idea that integration is the opposite of differentiation. Integration and anti-differentiation are really the same thing. And giving you an idea of how to, or giving you an opportunity to try to come up with some rules for integration. So today we're going to look at actual rules of integration. Now to do that, let's think back to rules of differentiation. So these are rules of differentiation. And differentiation and integration go hand in hand. Opposite operations, basically. So if we have a constant c, the derivative of that is 0. Okay, we're going to come back to this. If we have mx plus a constant, then the derivative of that is m. If we have x to the power of n, the derivative of that, using the power rule, bring the n down in front, decrease the exponent by 1, and we have nx to the power of n minus 1. Okay, we'll come back. We're going to start from there. So dealing with a constant first. So here we're calling our constant k. So this is our first example. The integral of k dx. Now remember some notation. This and this go together. The integral sign and the dx or dt or whatever you're with respect to goes here, and the function or the expression that you're dealing with goes in between those two. This means that we are going to integrate it. In order to do that, we need to anti-differentiate. Okay, so we've got a constant number. So for example, you might have to integrate the number 3 dx. Okay, so let's think the opposite way around. If I had a function f of x equals 3x, the derivative of that would be 3. Okay? Now, keep in mind though, if I had a function 3x plus 2, then the derivative of that, it's okay, that's just on the video, that alarm. They're just testing the alarms in the building while I am videoing. Okay, so the derivative of that function would be 3. Okay, if I had a function f of x equals 3x plus 500, the derivative would be 3. Okay, so basically no matter what this number is out here, and here it's 0, that number, then the derivative is 3. So whatever that constant number is out there doesn't matter, because when we differentiate it, we just get 3. So going the other direction, going here, we know then that this, the integral of 3, must be 3x plus some other number, and we're going to call that number c. We don't know what that other number is. Second rule, we're going to take the integral of x to the power of something. So for example, let's look at x to the power of 4 dx. Okay, now our rule up here, this is the rule. It's stating that what we need to do is add 1 to the exponent and divide by that bigger exponent. In other words, the exponent plus 1. Now in this case, n cannot be equal to -1. And the reason it can't be equal to -1 is because if it is, If it was, then we would have negative 1 plus 1 in our denominator, which would be 0, and we would be dividing by 0. So we are not able to do that. Okay, there's a different rule when we have something like that to happen. All right, so what do we do with this case then? We take this equals x, 4 is our n, add 1 to it, and divide that by this bigger exponent, so 5. 4 plus 1 if you want to write it that way. And then our constant, that's called the constant of integration, by the way, constant of integration. And we need that out at the end to represent some other number. We don't know what that number is, like I showed in the previous slide. So simplifying this, x to the power of 5, divide it by 5 plus c, or 1/5 x to the power of 5 plus c. Okay, now if we get into more complicated equations, for example, integral of x squared minus 2x plus 2 dx. Now, our properties of integrals tell us that this actually could equal this part, subtract the integral of 2x plus the integral of 2. So keep in mind, in other words, we're going to look at the integral of each of these terms separately from each other. So we can still follow this same rule up here. So here we would have x, 2 plus 1, divide it by that 2 plus 1, which is 3, subtract 2x. The power here is 1. We're going to increase it by 1 and divide by that bigger exponent, which is now 2, and 2x. Okay, now this same rule or same train of thought works here with this constant number. This would be x to the power of 0 if it had an x with it. We're increasing that by 1 and we're dividing by that bigger exponent. So you can see actually this works. The same rule of thumb, the same rule works. And of course we need our constant of integration out here. And simplifying x cubed, 1/3 x cubed, subtract x squared plus 2x plus c. Next example, the natural exponent. And that alarm is driving you nuts, I'm sure. It is driving me nuts too. However, we are all going to be safe in school this year because of it. So, integral of e to the power of x dx just equals e to the power of x plus that constant of integration c. So let's remember when we were taking the derivative, if I had f of x equals e to the power of x plus something else, maybe 1 out here, then when I took the derivative of that, it simply equaled e to the power of x, and that was it. So that one's pretty self-explanatory. That is the example. There we have it. Okay, here's a good one, and a good one to think about in the former rule, which was this rule here. We're going to talk about this next example using this rule, see what would happen, and see why there's a separate rule for this case. So first of all, if I were to change this into integral of x to the power of negative 1 dx, and then I use that rule back there where we increase the exponent by 1 and then divide by that bigger exponent, that exponent is now 0 plus c. So this is not possible. We all know that we cannot divide by 0. Okay, so that's not possible. So that's why there's a separate rule in this case when we have x in the denominator and the exponent is only 1. So this is what will happen. We'll take the natural log of that. It has to be the natural log of the absolute value of x so that we will be able to deal with any number positive or negative. So remember, when the natural log, a logarithm, that number can never be negative. Okay, so the number that we're logging can never be negative. So we need to remember that in this case, this is the rule. Okay, moving along. The integral of cos x dx is sine x plus our constant of integration. So remember, if we had f of x equals sine x plus some number, then the derivative was cos x. So the opposite is true. This is a rule. Similarly, the integral of sine x dx is negative cos x plus c. Now, if we think about if we had f of x equals cos x, then the derivative of that would be negative sine x. That's a rule that we know. Therefore, if we started off with an integral of a negative sine x dx, we would get cos x plus c. Okay, but for rules, we don't normally start with negative signs in there, so we have a positive here, and with this becomes negative over there. So that is that rule.